Okay. I hope the audio issues don't pop up again. Hopefully, if someone can just let me know if you're listening and it sounds absolutely awful to listen to, because I was testing the audio just then and for some reason there was like a lot of background noise and stuff. So hopefully it's not too bad. But yeah, let's get started. So welcome to the MATH3311 revision seminar. Yes, so today we're going through the first part of the seminar. So we'll only be covering up to around topic 6 or 7, and then the second half of our seminar is running this Sunday at, I believe it was 12 to 2 p.m. Which is only a few days before the test, but if you want to pop in and sort of just get reminded about some of the things you should be studying for, that would be good. Yeah, so if you're here, just sign the attendance form that's given by this QR code over here. And let's say if you're watching this a few days after it's been run, maybe in like the following week, just also sign the attendance form anyways, because it helps us out a lot. And yeah, so today I'm just gonna be going through the first 5 topics, so up to splines. And then Odin will be taking over to do Fourier analysis and maybe a bit of volatility and nonlinear equations. Now, there's 11 topics overall, but I'd say like having had a look at sort of all of the finals that are available to us, the first few topics don't really get tested, and the bulk of the finals really focuses on the last few topics. So when it comes to studying, I guess for, the first 5 topics or stuff, they only make up around 1 question max in the final. So that's, 20 marks out of the 80 marks. So the questions that you really want to get correct, but at the same time, we're not going to spend too long on the first 5 topics, just because they don't pop up in the finals at all. No, not at all. They don't pop up in the finals as much. So yeah, let's just sort of get started, and it's sort of just revision, maybe a few things that you've forgotten since the last few topics are quite content heavy, and it's been a while since, you might have done some of the earlier stuff. So let's talk about computing with real numbers, which is really just all of our stuff with floating point numbers. So remember just our definition of floating point numbers. So floating point numbers have this sort of form over here. So they have plus minus, so they can be signed or unsigned. They have this thing that I believe we call the significand or the mantissa over here, and then we have our exponent field. And I think one of the key things just with floating point numbers that you have to remember how to do is because our computers, since they store all of our numbers in binary, just be familiar with how to convert from binary to decimal and from decimal to binary and vice versa, because that could be a question that pops up. I'm not going to go through that too much today, because it is really just following like a set procedure. Yeah, so one of the questions that sort of just carry straight off just floating point arithmetic is 2020 question 1, so the very first question. And sort of this over here. So we're given a floating point representation. Now this obviously isn't the one the computer uses. This is a lot more of a simple sort of floating point scheme. And what we have to do over here is write down all the numbers that can be represented using this, and then find how many bits that we need to store these floating point numbers, real max, real min, and then machine epsilon. And let's just quickly knock b out of the way. So just one thing to keep in mind with floating point numbers is when we look at this, we need 1 bit for the sign, and then for each of the decimal places, we need 1 bit. And then for the exponent field, we need however many bits for that. So in like standard double precision, what we're used to is like 1 bit for the sign, 52 bits for the decimal places, and then we of course have 1 implied bit because of the 1 over here. And then usually we have 11 bits for the exponent field, so that's how we get our 64-bit double precision numbers. But in this one over here, we only have sort of 1 bit for this S over here, so for the sign, 1 bit for each of the decimal places, and then just 1 bit for the exponent field, because we can only choose from 0 or 1. So we only need 4 bits to store any of these floating point numbers. So now that we've knocked that out of the way, let's just go through writing down all the numbers that can be represented using this. And all we have to do is just look at like what can possibly fall inside the bracket, right? So the choices for things inside the bracket over here is 1.00, 1.01, but then also 1.10 and 1.11. And just keep in mind that this is all in binary notation, right? And then of course we have this 2 over here. So what we're going to do with that is, because we can only choose from 0 and 1, this is just times by 1 or times by 2. So what we can do is we can just find the decimal representation of these binary numbers over here, and then multiply them by 2 and then add a plus minus sign in front of all of them. And that's all the numbers that you can represent using this. And just the nice thing about like converting to binary and decimal is if you're really familiar with it, you can already probably recognize what these are. But otherwise, when you look at it, these are sort of 4 evenly spaced like binary numbers, right? So when you want to convert them into decimal, this is going to stay as 1, but then the rest are just going to be evenly spaced between 1 and 2. So what you end up getting is just this first chunk over here, right? 1 up to 1.75, right? So this over here was 1.00 in binary. This over here was 1.01, 1.10, 1.11 in binary. So you can see that they're just evenly spaced between 1 and 2. And how we get the remaining 4 over here is we're just going to double each one of these 4, right? So 1 times 2 gives us 2, 1.25 times by 2 gives us 2.5, and so forth. And then this part over here is just going to give us the plus minus, as I said earlier. Okay, what's the real max in this case? Well, real max is just defined as the largest positive like floating point number. So it's just going to be 3.5. And real min is the largest positive, also positive, floating point number. So it's just 1 in this case. And machine epsilon is just the value such that 1 plus that value is greater than 1. So if we have a look at this list over here, well, to get from 1 to the next largest value, we need to add 0.251, right? If we add anything less than that, it's still going to be 1 in the machine. So our epsilon is just 0.25. And that's all we're going to cover in this section. Like in the lectures, there was a lot more stuff. Of course, there was, for example, errors and significant figures and stuff. But what we'll do is we'll go through all of the stuff with matrices and stuff. And then sort of towards the end of this section, we'll go through some questions that bring in ideas from all of these topics. So we'll move on to the second topic now, which is all your stuff to do with norms mostly. So just recalling the definition of vector norm, I'm sure we're all really familiar with these one now because norms pop up in like every single math course. The norms, they just have these 3 properties over here. And then the norms that we want to be familiar with are our 1 norm, our 2 norm, and our infinity norms. But perhaps the more important one in this course is our matrix norms. Now, matrix norms also have the same properties, so, positive, definite triangle inequality, and this one over here. We also have this definition over here of a consistent matrix norm, but I think the most important thing that we have to know for this course is the definition of a subordinate matrix norm, which you might also sometimes hear referred to as like an induced matrix norm. And that's just this definition over here. So the P norm, so 1 norm, 2 norm, so 4th norm, of a matrix A is just given by this ratio of vector norms over here. And one of the really, one of the things that you can do with this, let's say you're doing a proof and you want to make your life a bit easier, is you can also just say, well, if we choose some vector x such that the P norm of that vector is equal to 1, then we can just define it in terms of the numerator over here. But yeah, regardless of which definition you use, this one over here or this one down here, that's a definition of your matrix norm. So anytime in an exam where they're like, define the 2 norm of matrix A, you're not gonna say perhaps this definition down here of the 2 norm, you're gonna give this definition here instead. If they ask for, the 1 norm of a matrix, you're not gonna say, well, that's the maximum column sum. You're gonna define it in terms of this over here. And so just on that note, there are some common matrix norms that you might be familiar with. So your 1 norm, your infinity norm, and then your 2 norm. And what's it called? There's also your Frobenius norm, which was covered inside the lectures. I don't have them on my slides over here, but that's also one that you might want to be familiar with. And I'll say the most important one to look at is probably your 2 norm over here with the square root of the largest eigenvalue. Basically just the largest singular value. In case you get asked a question that involves eigenvalues and has your 2 norm, you might have to use this. But just sort of carrying off matrix norms. We're not covering. Are we covering Black-Scholes today? I don't think we're covering Black-Scholes today, unless Odin will be covering that later on. But we will definitely be covering all of that stuff by our Sunday seminar. But today's one is sort of just stuff that everyone's probably familiar with, has done, for the lab tests and stuff. Just a reminder of all of that stuff. Okay, so let's have a question to do with our norms and matrices. So a lot of the work in this course for this earlier section is just being familiar with your linear algebra stuff. What property must Q satisfy to be an orthogonal matrix? Well, that's just Q times Q transpose is equal to the identity matrix. It's just this condition over here. State the definition of the subordinate 2 norm matrix of Q. That's just this thing over here, right? These ones might be a bit tricky, but once you know the hint behind them, it becomes really easy. So show that if Q is orthogonal, then the 2 norm of Q is 1. So we basically have to show that if Q is orthogonal, that this guy is equal to 1, right? And just starting off from this definition is what you want to do. And more specifically, you want to look at this guy over here, the numerator, right? And instead of working with the norm, what you want to do is you want to work with the inner product, right? So the square of the norm. And that's because the inner product in regards to the 2 norm is just the dot product, right? So if I want to look at this thing over here, that's just the dot product of QX, right? So that's just going to be QX transpose times QX, and then you can kind of sort of see where it's going from this, right? If you just use linear algebra, that's going to give you X transpose Q transpose QX, and since we know Q is orthogonal, we have this condition over here, so this is equal to the identity matrix. And just to be vigorous, I would go ahead and write that out. But then what that gives us is just X transpose X, and this is just the dot product of X, which is just the 2 norm squared, right? And what that basically tells us is then this 2 norm over here is just going to be equal to the max some arbitrary x, that's not the 0 vector, of this over here, which is just equal to 1. So once you know that instead of dealing with the norm, you want to deal with the dot product, then it becomes a lot easier and quite straightforward. And similarly, this one over here, showing that the inverse is 1, you're doing a very similar thing, right? So this time you're just going to have to prove something. You're going to just have to prove the same thing, but you're starting at the inverse. And the key here is if we're dealing with an orthogonal matrix Q, then the inverse is equal to the transpose. So this is just going to be equal to this, which is just the dot product, but this time we're dealing with the transpose of Q, and then transpose that again. And yeah, this becomes, it's kind of satisfying doing these because it's just linear algebra, and they are kind of fun to do. And this again is the identity, so it goes away. And then really similarly, I'm just going to be a bit lazy. That's going to land us at the same point, right? So once you know you want to deal with that inner product, that dot product over here, you want to show that they are equal, so then the norms are equal. Then it becomes really easy to prove these identities. Okay, let's move on and talk a bit about condition numbers. So condition numbers just tell us a bit about how, a bit about the errors that you might get. I forgot the word that I was looking for. But how accurate your answer might be. Let's say you're solving linear systems, you're finding determinants with a matrix A. What you want is a relatively small condition number for accurate answers. If your condition number is too large, I think the convention is if your condition number is larger than 1 on epsilon, which is roughly like 10 to the power 16, then your answer's not going to be really accurate, right? And in that case, you're going to want to do a bunch of matrix factorizations, whatever, to solve your systems in a nicer way. Condition number is just this definition over here, using whatever norm. And I think the one that, this is what I was talking about earlier. But one of the key things just to keep in mind is if you're dealing with a question and it has eigenvalues in it and it asks you to find a condition number, then you're going to be finding the 2 norm condition number. And all you're going to be doing is finding the ratio of the largest eigenvalue over the smallest eigenvalue, and taking the absolute value of those. And that's only also for symmetric matrix. So if in a question, it's like, oh, A is a symmetric matrix, A is a positive definite matrix, the question has something to do with eigenvalues, then this is probably the identity that you're using. So condition number is the largest eigenvalue and the smallest eigenvalue. And just one of the other things to remember, I haven't actually written out fully, but one of the things I know that was covered back in like week 1 or week 2 were those questions where it's like, oh, let's say you know A exactly, find how many significant figures the final answer will have, or questions like that. I think we'll go through one of those later, but that's just remembering that those relative error stuffs. And I think I included an example of that later, so I might jump and do that one later instead of covering the theory here without any context. Yeah, so we're really speeding through it. Okay, next let's talk about matrix structures and factorizations. Are these slides available somewhere? I will upload them up to the MathSoc website sometime. The problem with that is I've also done a really bad job at making the slides because they were admittedly last minute, so I wouldn't say they're the most comprehensive thing to use when studying. I've also like omitted a lot of the content that has been covered. How I sort of made these slides was I looked at all of the past papers, and especially with these first 5 topics, there's not a lot of questions on them. But I just chose the parts that sort of popped out the most. But yeah, I will fix these slides up a bit before I upload them to the MathSoc website, so it might take a bit longer. Matrix structures and factorizations. Before I get into that, just a few things to cover. So covariance and correlation matrices. The key things that I want to point out is that covariance and correlation matrices, they're symmetric. They're also positive semi-definite, and if they're non-singular, they're positive definite. And what that means is you can use things like Cholesky factorization on them. Alternatively, since they're symmetric, if you, when it comes to like storing symmetric matrices, you don't have to store the whole matrix, right? You can just store the lower triangular half because the upper triangular half is just going to be the same thing, right? So instead of taking n squared, like, what's the word I'm looking for? Instead of having to store like n squared things, all you have to store for these symmetric matrices is the lower triangular half, and that's just gonna be, well, there's n elements on this diagonal here, and you're adding all the elements down to that last diagonal, so it's m plus n minus 1 plus yada da 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 plus 1. And we know from high school maths that the sum of n, like 1 up to n elements, is n plus 1 on 2, right? So when you have a question and you have a symmetric matrix, and this pops up, you might want to think about like storing, instead of storing n squared elements, just storing n plus 1 on 2 elements, because you're just storing the lower triangular half. And you want to say that since we're just storing the lower triangular half, not the lower triangular half, just the lower triangular part, we just have this many elements that we want to store. But I think the most important thing to remember in this topic, in the lectures, they went through all of the fancy stuff, like all your special matrices, like your banded matrices, your diagonal matrices, your lower upper triangular matrices, your Toeplitz matrices, and like positive definite matrices and stuff. And definitely be familiar with those. But what we're gonna focus on here is just the factorizations and the properties of each of the matrices in these factorizations. Because the whole goal with these factorizations is to take a matrix like A, for example, that doesn't have any sort of special structure, and to break it down into these other matrices that do have special structures that are nicer and more efficient to work with. So I think the 4 factorizations that are covered in this course is just your LU factorization, Cholesky factorization, QR factorization, and singular value decomposition. I don't think I have missed any of them. It's just those 4 factorizations. One thing to remember is when you're dealing with lower triangular matrices, you're using forward substitution, which is n squared flops, and upper triangular matrices, same amount of flops, so you're dealing with back substitution. And the reason I point this out is because if you're like answering a question and they're like, how are you going to solve this system? Then you have to just remember lower triangular, well, that's forward substitution. It makes a lot of sense, right? Because your matrix kind of looks like this, right? So you're obviously substituting downwards, so it's forward substitution. And the same applies to back substitution with your upper triangular matrices. So let's just quickly remind you of all these factorizations. So LU factorization is like our Computational Gaussian elimination factorization. So what we're doing is we're decomposing it into LU. L is unit lower triangular, right? And U is the upper triangular matrix. Typically with LU factorization, we're also going to get our permutation matrix. And that's just because what our permutation matrix does, remember, is it just swaps the rows of A. And like when you think about how you solve like a linear system using Gaussian elimination, it's a lot easier sometimes when you have to swap the rows. So typically with LU factorization, you're going to get your permutation matrix. LU factorization, you're solving, let's say you're solving this system over here. What we do is we use forward substitution to solve this and then back substitution to solve this. If you have the permutation matrix, all you're going to do is just chuck your permutation matrix out the front of B over here. I think that's right. Yes, that's right. That's LU factorization. Let's then move on to Cholesky factorization. So Cholesky factorization is the one that we use for symmetric and positive definite matrices. So if there's a symmetric and positive definite matrix, we're using Cholesky factorization. And in Cholesky factorization, key thing is we're decomposing it into an upper triangular matrix. One of the other things with Cholesky factorization is, and I guess one of the issues with it is when you use it, you end up squaring the condition number because of this thing over here, the R transpose times R. So that's a sort of issue potentially with it. Cholesky factorization, it's the easiest thing to check for a positive definite matrix. If the Cholesky factorization exists, then it is positive definite. Yeah, that's all I have to say. Since it's upper triangular, we're dealing with back substitution. Yeah, okay. QR factorization, we're breaking it down into an orthogonal matrix and an upper triangular matrix. I write it in this form over here because when you use QR factorization on like a non-square matrix, like an m by n matrix, then you have to sort of make up for the dimensions using 0 elements. Let's say you have a square matrix, then it's just going to be A is equal to QR, right? And the same thing happens with singular value decomposition. So just remember, singular value decomposition, the U and V, the unitary matrices, the orthogonal matrices, and sigma over there is your diagonal matrix with all your singular values, your ordered singular values. I'm sure many of us might remember singular value decomposition from MATH3311 or 2501. Yeah, it's a pain in the ass to compute. Luckily, we don't have to do that. Yeah, so basically with these factorizations, just remember like all the properties. So like, is Q, what's Q? Well, Q is orthogonal. In Cholesky factorization, we have an upper triangular matrix. In singular value decomposition, your U and your V, the orthogonal matrices. Just remember that who am I and why do I know everything? I do not know everything. That's a big disclaimer. I do not know everything. So with these revision seminars, all I'm basically trying to do is just remind people of some of the stuff that they have to study, but it is not comprehensive. And am I qualified to be here? Probably not. But yeah, let's just keep on going. So what we're gonna do now is we're gonna just go through a few questions that combine all of these stuff, right? And I think the key thing to keep in mind is the first 5-ish topics, they only take up like a maximum of 20 marks in the exam, but you can get like asked like anything from within all the topics. So you want to be still really familiar with all of that stuff. But like these topics have been covered a lot in like, for example, the lab tests or the assignments. So hopefully we'll be quite familiar with a lot of this stuff. Okay, so for example, we have 2018 question 1. Okay, we have A, it's a square matrix. We want to write down the QRD composition of A. Well, we just went through that earlier. A is just going to be equal to QR. Q is going to be orthogonal. R is our... Man, I just had a mind blank. Oh no, that was really bad. It's upper triangular. Upper triangular matrix. So that's our QR decomposition. Since we're dealing with a square matrix n by n, all of these other matrices, like this is Q is going to be an n by n matrix, R is going to be an n by n matrix. Okay, B, assume that you've already computed the QR decomposition of A. State an efficient way of computing that thing over there. And then C is also really similar, just this time you're dealing with the inverse of A transpose A. And the thing with these exercises is they're all just reliant on some relatively simple linear algebra. So how you go about doing these questions is you just start off with the thing that you have to compute and you substitute like all the A's with QR instead, right? So this is now going to be B transpose, well, instead of A transpose, we're just going to have QR transpose times QR B. And the key thing that we're sort of working towards here is because Q is orthogonal, we sort of went through this earlier, we're looking for any time these identities show up, right? Because then we can simplify our expression. And if we remember just from algebra, if we take the transpose of this thing in brackets, that's just gonna give us this instead. So you sort of reverse the order. And then QRB. This is our identity matrix. So I would say just be like vigorous and write out the whole thing, even though it's really annoying. I should probably, okay, I'm not gonna be bothered to do that. B transpose R B. And what we notice over here is that this is actually just RB transpose, right? So anytime you see like something that looks like this, you know sort of something's going on there. And what we get is just to this point over here, and that's just the dot product of RB. So if we want to compute this expression over here, instead of calculating and chucking this whole thing into MATLAB, we just want to compute, let's say let y equal to RB. And that's sort of really nice because R is just our upper triangular matrix. So instead of working with A, which is this, whole matrix with no special structure, we're just dealing with something nice like this instead. And then we want to just calculate y transpose y, right? Now, C is gonna follow off a really similar thing. So once you get to some point in the proof of C, it's gonna be basically exactly the same as, not exactly the same, what am I talking about? It's basically just an exercise in linear algebra. But I think the key thing that you have to keep in mind over here is with your finding the inverse and brackets, it's basically the same as like taking the transpose of a bracket. You know what, let me work through this one as well. So I just don't have space. Let's start it over here. Okay, so C transpose A, take the inverse of that C. This time I'm not gonna just chuck it into one expression because I have a feeling that's gonna get really annoying. So let's start off just with this expression over here. A transpose A, the inverse of that. Well, that's just gonna be what? A, the inverse of A. Oh, I should probably, actually let's establish something earlier here. Let's figure out what the inverse of A actually looks like, because we're gonna be able to do something nice with that, right? So the inverse of A is just the inverse of our QR factorization, which if we just apply this, we're gonna get the inverse of R times the inverse of Q. But since Q is an orthogonal matrix, what we're actually gonna be working with is just the transpose of Q. So that's gonna help us a bit. Actually, I don't know if it will help us, but let's just establish that first. Okay, and then let's figure out what A transpose A inverse might look like. Well, that's just gonna be the inverse of A, and then the inverse transpose of A. And that's just gonna be what? R inverse Q transpose. And then we wanna find this as well. So we're gonna transpose this guy over here. So that's, oh, we wouldn't actually need to use that thing, that orthogonal identity earlier. Okay, so then we get this, and similarly we can get rid of the Q transpose Q's. So that's just gonna be R inverse transpose. And then what we can do is we can chuck this back into here. So that will now become, okay, I'm doing this on the spot, and this is most definitely not how I would lay out in the test, but it is what it is. So now we have this expression over here. And what we notice again is something really similar to the end of this one over here, right? It's just a bit trickier because we have like inverse transpose and all of that funky stuff happening. But this over here is just a transpose of the latter half of the expression. So this is just R inverse transpose C multiplied by that. Okay, I should write this out better. But now we have this thing over here. So it comes back to like a really similar thing as in part B. What we just have to do is we have to compute like R inverse transpose C. And then, wait. Sorry. I meant to put a transpose over there. And then calculate that, right? So what we can do, this isn't like quite as simple as just having RB transpose and like chucking RB, which is just matrix multiplication, into, you know, MATLAB or Python, because this time we actually have the inverse of R. So we also have to figure out how we might go about computing that. But that's also pretty sort of simple. Let's say we just have, okay, this is really messy. Let's just copy that down here. Let's say we set z is equal to that expression, R inverse transpose C. Then what we can just do is, well, this is just a system of equations, which is RTZ is equal to C. R is our upper triangular matrix. So if we take a upper triangular matrix and then we find the transpose of that, that would be lower triangular, right? And then what we would have to do is use forward substitution. Yeah, forward substitution to solve for z. And then that will give us the thing that we need to multiply. Then we compute, after we find z, then we just have to compute z transpose z, right? Okay, that was a bit messy. I think there's like solutions for this stuff anyways on the middle. So you'll probably find something a lot nicer written out there. I did have a brief look at it to make sure that my solution was correct. So yeah. Okay. 2014. Question 1. So this is sort of more working with all the stuff with calculating speed and flops and all of that stuff. So first of all, in the exams that I've seen more recently, we don't actually get this table. So it would be good to remember the flops of all the factorizations. Going into the test, I'm pretty sure we can bring in, like, okay, these aren't that hard to remember, but if you want and you forget, it's only gonna take up like a really small portion of the cheat sheet that I think we're allowed to bring in. Yeah, so let's just jump into this question. Okay, so sorry, I'm just reading through it now. Let's answer A. So what's the largest correlation matrix K that can be stored in the cache memory, which is our 12 megabytes over here? Okay, so the thing with this question is there's multiple ways you can go about answering it. So the first thing, and probably the thing that you're most inclined to do, is just say, well, K is n by n, right? So we're using double precision. Each element is going to take 8 bytes, right? Also, just remembering, if you're dealing with real numbers, it's 8. If it's complex, then you're going to need 16. But I haven't seen too many questions dealing with that. But your first instinct might be to be like, well, we have 8n squared, and then since we have 12 megabytes, well, that's 12 times 2 to the power of 20. So also just remembering kilobytes is 2 to the power of 10, megabytes is 2 to the power of 20, and then gigabytes is 2 to the power of 30. That's most of the ones that you have to remember. The scale goes on into like weird stuff like petabytes and exabytes as well. The key thing just to remember is your kilobytes, megabytes, and gigabytes. So your first instinct might be to solve this equation over here, and that would give you something like 12, whatever that, I don't have my calculator with me, but I think this was, if you round it to, like if you round it down to the nearest whole number, that's going to give you n is equal to 1254 if you solve this. But alternatively, since this is a correlation matrix, I mentioned earlier, our correlation matrices, there's symmetric, right? In fact, in like, if you do like stats courses and stuff, sometimes when you look at your correlation matrix, they only show you half the correlation matrix, because that's all you need. Then what's it called? what we can instead do is we can just store the lower triangular half of our matrix. And sort of like what I mentioned earlier, that means we only have to store n plus 1 on 2 elements instead of n squared elements. So instead, we're solving this equation over here. Now, this gets a bit annoying because then it becomes like 4n squared plus n is equal to this. So it's annoying and it's quadratic. So what you can instead do is, instead of solving the whole thing, you can be like, oh, that's roughly 4n squared, right? Like that's the dominating term over there. So you can just roughly solve this equation over here instead. And that will get you, I don't have my calculator on me. That will get you some number. Give me a second, let me calculate that. It'll give you, n will be just the square root of this number over here. I'm so sorry, I haven't chucked this into my calculator. But then what you want to take is just the nearest whole number, rounding down. Not that it really matters because we've already approximated it so much. And that would be our n instead. So there's two ways of doing it. I think I'm actually not entirely sure which one would be accepted, but I think as long as you justify sort of what's happening, then you should get the marks, right? So if you go with the second method, then you just have to explain what's a correlation matrix, it's symmetric, we're storing the lower triangular half. Yeah, okay. Estimate the speed of the workspace in G flops per second. Well, that's pretty straightforward. We have 3 gigahertz, 6 cores. So all we have to do is 3 times 6, and then each can do 4 floating point operations per clock cycle. So multiply that by 4, and that's going to get us 72 gigaflops. Yeah, per second. Okay, let's do C now. So what's the largest value of n so that 100 linear systems can be solved in 1 hour on this workstation? Now, the first thing you have to figure out is, how are we going to, like, how many flops is one linear system going to take? Well, sort of what I stressed earlier about these correlation matrices is, if you have a non-singular correlation or covariance matrix, you are going to use Cholesky factorization because they will be positive definite and they will be symmetric. So Cholesky factorization is just n cubed on 3. So all we have to solve is just 100 n cubed on 3 is equal to, well, 1 hour is 3,600 seconds. And then we have 72 gigaflops. And just a key thing to remember when you're dealing with gigaflops is it's 10 to the power of 9. So you're going to do 10 to the power of 9, and then you're going to solve this. That is going to give you your value of n. And I also don't have that on me right now. Sorry. I would check into a calculator, but I also forgot my calculator somewhere, so I don't have my calculator on me. But yeah, pretty easy to solve. And then similarly, all you have to do in D is just explain that you're using Cholesky factorization, right? So say, since we're dealing with a non-singular correlation matrix, it's positive definite, we can use Cholesky factorization. When we're using Cholesky factorization, we're going to be, well, our K is now going to become R transpose R, right? So then when we're solving using Cholesky factorization, since these are upper triangular matrices, we're going to be using back substitution. So then just sort of write that out. Yeah. Oh, I meant, wait. No, I messed that up. there's also transpose over here. So it would be, Cholesky factorization is forward substitution and then back substitution. So just write that out. Yeah. Wait, is it forward and the back? The RX forward upper triangular. Yes, forward and the back substitution for Cholesky factorization. Okay, last question for this chunk that we're gonna go through, 2016 question 1. So we have C n by n covariance matrix. So yay, again, we have, actually, that's the first question. Is the matrix C positive definite? Now, it's not enough to have a covariance matrix and then say that's positive definite, right? Because covariance matrices, all they have is positive semi-definite, right? So they're not necessarily strictly positive definite. But if we just remember back to the definition of positive definite, that's just all positive eigenvalues. And we can see from this over here that our smallest eigenvalue is positive. So all our eigenvalues are positive, C is positive definite. Just on another note for positive definite, I haven't seen too many questions on this, but just remember your other tests for positive definite. So I believe like the diagonal dominance test. So basically if the diagonal is of greater magnitude than the sum of the absolute values of all of the other non-diagonal elements on the row, then there's diagonal dominance, and then you have a positive definite matrix. That's also a one-way thing. So if you have a positive definite matrix, it might not be diagonally dominant. But I haven't seen any past questions testing that, but that's also just something to keep in mind. But again, easiest test for positive definite is checking eigenvalues, checking if there's a Cholesky factorization. Okay. B, the command determinant of C yields 0. Is this correct? And why? Well, we know that our determinant is just determinant's just the product of all your eigenvalues. But since we have all positive eigenvalues, then our determinant has to be greater than 0. So what this is basically saying is, because our determinant is so small, in a floating point representation, it just becomes 0. And MATLAB just stores it as 0. This also tells us that our condition number is probably pretty big. Now, we're finding the condition number of the matrix C in an appropriate norm. This was something I said earlier. It was really important. If you have eigenvalues and you're finding the condition number, you're finding the 2 norm condition number, and it's just the biggest eigenvalue on the smallest eigenvalue. So C, your kappa 2 of C is just going to be 3.6 times 10 to the power of 5 on 4.0 times 10 to the power of negative 4. That's going to get you something like e times 10 to the power of 8. So it's a pretty big condition number. Also just remember, this is like the absolute values as well. So it will always be like a positive ratio. So that is C. And looking at D, that's sort of what I was talking about earlier, like many 10 minutes ago, about remembering how to answer these questions. So it can also go the other way. So it might also be like, oh, C is known exactly, B is known to this many decimal places, find the relative accuracy of your solution. Or it could be like this one. The key thing to remember is the formula that we have, which is that the relative error of x is just equal to the condition number. The condition number, this time we're dealing with the 2 norm, so we can just use that, of the relative error of C plus the relative error of B, and we just use these thingamabobs to denote that. The elements of C are known exactly, so what we can say is the relative error is epsilon, which is roughly, I'm just going to substitute this in, 9 times 10 to the power of 8, which is roughly, always just use 2.2 times 10 to the power of negative 16. You just have to remember that. Plus the relative error of B. And the relative error of X, since X must have at least 4 significant figures, if we remember that, that's basically just saying that the relative error has to be less than 0.5 times 10 to the negative 4. So depending on however many significant figures you want, you're going to change the 4, right? If you want 10 significant figures, that becomes 10. If you want 1 significant figure, that becomes 1. Yeah, so basically what we want to solve is this, and we want to make sure that it is less than that thing that I wrote up earlier, less than 0.5 times 10 to the negative 4. So if we just rearrange that, so if we, let me just do that. What we are gonna wind up with is 0.5 on 9 is gonna give us 1 on 18. 1 on 18, and then that's gonna be times 10 to the negative 12. So I'm just dividing by 9 times 10 to the power of a over here. And then we will just subtract 2.2 times 10 to the power 16. Oh, what have I done? That's supposed to be a 12, not a 2. Negative 12. So the relative error of B has to be less than this thing over here, but we don't want just this. We have to figure out like how many significant figures we want. And what we know about this is gonna be less than, this will be less than 0.5 times 10 to the power of negative 13, because this is really small, so we don't really have to worry about it, and we can just look at the like this thing over here. So we have to know B to at least have to know B to at least 13 sig figs. So a lot of like these questions, you just have to remember certain things. So for example, just remember this formula over here. Remember that whole thing with significant figures. So less than 0.5 times 10 to the power of negative k for k significant figures. Remember that if you know the matrix exactly, you're going to use epsilon, and the value you should use for epsilon, if it's not given, is 2.2 times 10 to the negative 16. I think that's correct. I think that's the number you're supposed to use. Yeah. So that's what you have to remember when you're solving those sig fig questions. Okay, next we're going to move on to data fitting, and we're not going to do a lot in data fitting. The reason we're not going to do a lot in data fitting is because this is mostly just your least squares problems. And I know that like least squares was tested a lot in like the lab tests, and it's like a pretty standard procedure that I think most of us should be familiar with. You just have your matrix and then you backslash it in MATLAB. The main thing I would say is like constructing your matrix, but I'm sure like we needed to do in the lab test, so I'm sure most of us know how to do it. So I'm not going to cover data fitting. Also, looking in the finals, there wasn't too many questions on this, but the questions that did have to do with it, it's more just about being comfortable with your linear algebra. Yeah, Similarly with splines, I'm not gonna go too much into sparse matrices. I'm sure we all know like how to calculate sparsity. And it becomes a bit more important like with your spy plots and some of the other topics, so that's not covered in this section. The main thing with splines is like know what a spline is. So if you have to explain a spline, be like, well, it's a piecewise polynomial of small degree. So if you have a cubic spline, then all the piecewise polynomials have degree 3. You can also have quadratic splines where all the polynomials are going to have degree 2, right? Just like small degrees. That sort of just interpolates the function, right? And I think the key things that you just want to remember are the different boundary conditions, and be really familiar with these 3 main boundary conditions. So your natural splines, your clamp splines, and your not a knot splines. Because from what I've seen, most of the questions with splines test like your understanding of sort of what's going on. So they might ask you to explain what a spline is. Okay, I shouldn't say that. From the past papers, the questions were like, explain what a spline is, explain why these 2 different splines give different results. So they're really explanation questions. I don't know if they're gonna pop up again. I haven't actually seen, like we don't have access to the finals from 2021 or 2022, so I don't know if they've come up with new, more challenging questions to do with splines. One of the like only computational questions I could find with splines was question 2 from 2020. But with these, like with this one at least, it's basically just solving a bunch of like equations simultaneously. Not even like, we're just given like 6 conditions over here, and you just have to solve using all those conditions until you find the coefficient. So it's pretty straightforward. And then the other spline questions I've seen are just about interpreting the results. But who knows what we might get. I could go through this question over here. It would be the last question I go through, and yeah, I wouldn't say we're too over time, so I just go through it. But this really is like, it's pretty straightforward. It's just solving equations. And there's not a lot of like content or like theoretical things behind it. But yeah, so we have our, oopsies, wrong thing. We have our spline. It's piecewise, it has 2 parts. So the first part is this, and that's for -1 to t to 0. And then the second part of our spline is just the same thing. They're both quadratic. T squared from 0 up to t up to 1. And then we have what, 1, 2, 3, 4, 5, 6. We have 6 conditions. So we're given like the 6 conditions that I'm talking about, I guess, instead of writing them all out. This one over here, this one over here, this one over here. Key thing to point out is this doesn't like tell us S0 or S1, but since this is dealing with the point at t is equal to -1, then this is obviously S0 is equal to 0. And similarly, all of these points over here give us conditions, right? So the first point tells us that S at -1 is equal to 1. The second point tells us that S at 0 is equal to 2. And the third point tells us that S of 1 is equal to 0. And all you have to do is use those 3 conditions and solve this. Whoopsies, I made a mistake. That should be just less than t. So it's not really theory, it's just solving equations. But we can do it really quickly, it won't take too long. So if we look at the first condition, we're setting t is equal to 0. So if we set t is equal to 0, then we're just gonna end up with a0 is and A1, right? So the first condition gives us that A0 is equal to A1, and that is also equal to our first bit of the spline, our first piecewise polynomial evaluated at 0, which we know is equal to 2 because they've given that to us. So we found A0 is equal to A1 is equal to 2. We can look at the second condition over here now. I should have probably labeled these different things. Let's just get rid of that. That's our first condition. Second condition, third condition, fourth, fifth, sixth. So this first one over here used our fourth condition plus the first condition. Let's have a look at our second condition. This time we're taking the derivative of these two, and they are equal to each other. So if we take the derivative and then we set the t equal to 0, that's just going to give us b0 and b1. So the second condition gives us that b0 is equal to b1, right? So we just keep that in mind, and we can't do anything else from it for now. So then let's have a look at the third condition. Well, the third condition tells us that the derivative just of SO evaluated at -1 is equal to 0. So the derivative is just BO plus 2C0T. So I should probably write that out. B0 plus 2C0T. And then if you evaluate that at -1 and set it equal to 0, that's just going to give you the condition B0 minus 2C0 is equal to 0, right? So that's all we get from the third condition. Which one have we not used so far? We haven't used our 1, 2, 3, 4 fifth condition. Do we want to use that one? No, what am I going on? I think I messed up. That shouldn't be 4. We've used our fifth one. So let's have a look at this condition over here, right? So this time, again, we're at -1, so we're going to be dealing with S0. And if we evaluate this whole thing over here at -1, then we're going to get that equal to 1, right? So that's just going to be A0. Well, we know A0 is equal to 2 already, so we can just put 2. Minus B0 plus C0 is equal to 1. And boom, this is a simultaneous equation now, just in terms of B0 and C0. And if you solve that, let me look at that really hard. That's going to give you B0 is equal to 2 and C0 is equal to 1. Yeah. And then all we haven't used now, we've used 1, 2, 3, 4, 5. All we need to do is then substitute all of this into 6, our last condition. So this time t is equal to 1, so we're dealing with the second part of our spline. So A1 plus B1 plus C1 is equal to 0. And all that's left is we have, of this, we know B1 is equal to 2. All we're missing is C1. We can substitute the rest in. So that gives us C1 is equal to -4. And we found all the coefficients. So this wasn't really a question about splines at all. This was just a question about solving equations simultaneously. What I'm going to do now is I'm going to pass on to Odin, who's going to cover the more tricky, funky stuff, like Fourier analysis and maybe implied volatility and nonlinear equations. But all of the more challenging, hefty stuff will be covered on Sunday as well. So I'll just check that Odin is good to go, and then hand over to him. You know what I'm going to do? I'm going to just leave it on this slide for you. Please sign the attendance form if you haven't. I will post the slides after I fix them up a bit. And I'll post like the slides after today, but then after Sunday, they should be fixed up and have the later topics that we're covering then as well. So yeah, the slides will be posted. They will be on the MathSoc website. Yeah, okay.
Okay, hopefully the audio is working as well. Cool. Okay, hopefully the audio is working as well. All right, hello everyone. So I'll probably present mostly Fourier analysis and FFT today, and we might get around to Black-Scholes and nonlinear equations if we have time, but otherwise we'll do that on Sunday. Cool. So yeah, the basic reason for doing Fourier analysis of a time series, a sequence of values, is we expect there to be sort of periodicity in the time series. So that might look like, every 3 months an event occurs in a financial market, and that has a particular effect on some econometric number that we want to detect. And we do Fourier analysis to find out how often this regularly spaced impulse is happening. So the basic idea is that we will take our time series and try to write it as a sum of sines, cosines, and a constant term. And if we sort of imagine the time series as a continuous function of time, obviously we can write like an infinite series to represent that, but usually we only have a finite number of samples. And so that's the point of the discrete Fourier transform. And then, so the DFT is naively n-squared operations, which means that it's pretty slow when n is quite large, n being the number of samples that we're processing. But FFT thankfully can reduce it to O of n log n time complexity, which is quite a bit faster for large n. So in the sort of past papers, it mostly focuses on the DFT. The continuous version of the Fourier transform doesn't come up as much. But yeah, so the DFT is basically just this sum in terms of complex numbers. And I guess this k here is sort of representing the frequency component that we're looking at. And so the DFT of a vector, a sequence, is just going to be another sequence, another vector that is going to, each element is going to represent a different periodic component of the original sequence. So if I go into MATLAB here and I go like y is 1 to 10, say, if I take FFT of y, it'll just be another vector with 10 elements. And each of these will represent some different periodic component, with the first one just being the constant term. Yeah, so I guess the point of doing this is so we can write out this trigonometric representation of the original sequence. And hopefully by representing it in this trigonometric form, we will implicitly find like which of these trigonometric terms is most significant, and then this k in each term is going to determine the frequency of that term. And this is going to tell us basically whichever frequency has the most significant coefficients is probably the frequency at which this impulse we're trying to detect is happening. So I guess the way in practice that you would detect this is by looking at the power spectrum of the Fourier transform. So you take the Fourier transform of your sequence, you square the absolute magnitude of each complex element in the vector, and then for technical reasons, I guess, we're going to normalize it by dividing it by the length of the sequence. And I guess the reason for normalizing it this way is so we can compare sort of, if we have two different frequencies sampled at different rates, then potentially we might want to compare the power spectrum for both of them. And obviously, if there's a different number of samples, that will have an effect on how big you might expect it to be. So this question is from the 2015 paper, and it's basically just showing a graph of various graphs related to a time series. So we have this time series here in the first graph that has an exponential trend. After we remove that exponential trend, it still seems to have, you can sort of see a periodic-ish pattern going on here. And if we look at the power spectrum, we can see that it looks like, there's something consistently happening once every year, and also something consistently happening once every month, so 12 times a year. And so I guess we can justify or refute the claim that the data has both yearly and monthly cycles of roughly the same intensity. Well, if we look at the power spectrum, they're roughly the same height at 1 and at 12. So yeah, I guess this is a reasonable thing to say, is that there's a annual cycle and a monthly cycle in this time series. So I guess I'll go through some properties of the discrete Fourier transform that come up in the past papers. So one thing is, if I look at this Fourier transform, you'll notice that this first coefficient, this first element of the vector here, is the complex conjugate of this last element here. So here we have -5 plus 15i. Here we have -5 minus 15i. And again, if we go here, we have -5 minus 6i. Here we have -5 plus 6i. So this is sort of the relationship that this is talking about. And if we want to prove this is true in general, it's basically just algebraic manipulation. So we can use the definition of the Fourier transform vector, and we'll just substitute m minus k in place of k in the definition. And then this sort of splits out into, we have this term here where the frequency is n, and then this term here where the frequency is minus k, and this minus and this minus turn into a plus. Yeah, and so I guess because we have n over n here, this ends up just being an integer multiple of, so this is an integer multiple of 2 pi. And so if we have this exponent, which is an integer multiple of 2 pi I, that's just going to be 1. And then over here, this is going to stay the same, but because we have e to the plus some real number, that's the conjugate of e to the minus the same real number. And then because our original sequence was real number valued, this being, I guess, conjugated means that the whole thing is conjugated. And we can see that this yk is essentially the, I guess this sum here is by definition the conjugate of the kth element of the Fourier transform. So yeah, it's pretty much just algebra to figure that out. So I guess we can look at the inverse transform as well. So I guess we can try this in MATLAB. We have the inverse transform of the Fourier transform. And we can see that these are all basically the same. They're very, very close. So yeah, I guess this is, it's useful if you have, like, I guess if you had a power spectrum, or it's, I guess if you have the Fourier transform of a sequence, you can sort of reconstruct the original sequence. And there is actually a question from 2018 on proving that this is true, which seems maybe a little bit scary at first, but I guess if we look at this claim here that we want to prove, we have this Fourier transform element inside this sum. Essentially, we can use the definition of that Fourier transform element. And so if we plug in the definition here, we get sort of a nested summation. And then so, yeah, if we bring this term into this term, we get this sort of difference in the exponent j minus m. And then I guess we can move this summation inside this summation because these just these have no dependence on k. So if we move this summation inside, then we get I guess 1 on n times this here. And I guess the thing to notice is that when j is equal to m, so j here is just a fixed number. When j is equal to m in this summation, this is going to be equal to 1 because we get e to the 0, which is 1. And then we have, n terms in this summation. So this is going to be n times 1 divided by n. So this yj term is going to stay there. But if we use this geometric series formula for the sum end here not being 1, we're going to, I guess you can, if you do the algebra, you recover that this sum should just turn out to be 0. And so all these terms where m is not equal to j will also be 0. And so we just get yj here. And that sort of proves this equality that we wanted. Cool. So I guess we'll cover, yes, hopefully we can get through a fair chunk of this chapter. So I guess I'll go over a little bit of the finance background as well. So obviously, if we have a stock price, it's going to vary, and we don't, if we knew how it was going to vary, if it was going to go up or down, I guess we could make some money by, if it's going to go up, we should buy it now. If it's going to go down, we should sell it now. And of course, up and down is sort of relative to the interest rate. If it's going up by less than the interest rate, we're probably better off putting our money in a deposit account or something like that. but with that technical detail aside, typically the stock price is going to move sort of randomly. And that's just because if it was moving in a very deterministic way, it would be potentially we would have an arbitrage opportunity in the sense that we know where it's going to move and we can trade based on that. But because of that effect, people will tend to move the price up to a reasonable price from which we don't know any more about sort of the future expectation. So if everybody thinks it's going to go up, it will sort of be at a higher price to begin with. And because of this, we sort of have this, I guess the stock price will tend to follow a jumpy sort of random pattern. And one way to model this is with a geometric Brownian motion, which I guess is a particular stochastic differential equation that defines the stochastic process that the stock price should follow. And I guess the reason for having this model, even though it doesn't tell us whether the stock price is going to go up or down, it does potentially tell us things about derivative assets whose value depends on future values of the stock price. So one example of a derivative asset is a European call option, which basically it's a contract with a fixed strike price and a fixed expiry time. And it says that at the expiry time, if the person holding the asset wants to, they can buy the stock for a pre-nominated strike price K that might be different to the market price. And I guess the reason it's an option is because you have the option to buy or not buy depending on what is more profitable for you. And so I guess at the expiry time, the value of the option is going to be the more profitable of not using the option or using the option. And if you use the option, well, you pay the strike price to acquire the stock, but then you can sell it for the current market price. So because of this, in the event where the market price is higher than the strike price, we'll make a profit by exercising the option. If it's lower, we don't have to. So we'll just make zero profit and zero loss. And for a put option, it's sort of the opposite. We can sell, so we'll do that if the stock price is lower than the strike price, and otherwise we'll do nothing. So someone asks, who is paying the difference between the strike price and the market price? So I guess the writer of the option will have to, they have an obligation to provide 1 unit of the stock or how many units of the stock in the event that the holder of the option chooses to exercise it. And so I guess because of this, if an exercise does take place, the writer of the option will need to acquire the stock for price ST in the case of a call option. But they will also get compensated by an amount which is the strike price. So I guess the cash flows here will sort of go, the net cash flow for the writer is just the negative of the net cash flow for the holder, whether that is 0 or whether it's ST minus K. And that just depends on whether the holder chooses to exercise. And whether they should exercise is just a function of this difference, whether it's positive or negative. So I guess the reason for constructing this stochastic model of the stock price is that we don't actually know what ST is going to be until we get to the date of expiry. Until then, it's going to sort of follow potentially a diffusion process or some other kind of process But if we specify a model for like how it will behave statistically, then we can compute how much it should be worth. And so if we assume this geometric Brownian motion model, there's a hedging argument that was presented in the final lecture of the course that basically derives a fair value for the call option by thinking about how can we construct a portfolio in terms of the option and a future or the stock. How can we construct a portfolio that has no risk, but so has no risk of downside loss, but potentially has upside gain. And so this is the delta hedging argument that was covered in week 10. But if the market is sort of priced fairly, there shouldn't be this opportunity to make free money. So rather than being a positive profit, since it can't be a negative profit, the way this portfolio is constructed, it should be a profit of exactly zero. And by arguing this way, we sort of get the arbitrage-free derivation of the fair value of the option. But that is, I guess, that is according to this assumption that we made about the statistical model for the stock price. Yeah, so we're gonna basically have this function of all of the data that we have, the current stock price, the time until expiry, the interest rate, the market volatility, and the strike price. And so we can construct this argument for the value of a call option. We might also be interested in the value of the put option with the same time until expiry, the same strike price, and the same market parameters on the same stock. And it turns out that because the option gives the holder because the call option gives the holder the right to buy when it's profitable for them, and the put option gives the holder the right to sell when it is profitable for them to sell at the strike price. If you have party A giving party B a call option and taking a put option from party B, I guess the net effect of that pair of transactions is going to be essentially the way the cash flows work out is going to be that party A has given a future for the underlying stock to party B. And if we follow this logic through, we get a value for a fair Black-Scholes value for the put option in terms of the call option and the forward price. Cool. Yes, so if we look at all these parameters here, the stock price, time to expiry, interest rate, strike price, the only one that we don't currently know, well, if we assume the interest rate is fixed, we know the stock price currently because we can just look at the market. We know the time to expiry and the strike price because we can just read the options contract. We don't know this is called the volatility parameter. And this is basically governing, I guess, the way that the variance of the geometric Brownian motion evolves over time. And so I guess because this is unknown, and we sort of need to estimate this if we're going to deduce a fair value for the option, we can sort of also go the other way, where if we know the current market price for the option and we assume that it's fair, we can deduce a value for what the volatility would have to be in order for the Black-Scholes model to give the market price as the fair value of the option. And it turns out that this has a unique solution for the volatility, so long as we assume that the volatility is positive, or I guess non-negative. And so we end up with this equation for implied volatility, where we take the market price and, we solve the Black-Scholes model, given all the details, including the unknown volatility. We solve this equation and we can compute the implied volatility using any sort of root finding algorithm. Could be Newton's method, could be bisection, secant method, something else. So I guess this this problem of estimating the implied volatility is what's going to lead later on to the motivation for, among other things, the motivation for finding roots of nonlinear equations. And we may get to that today, depending on how we go for time. So I guess the second part of this chapter 7, or the second part of chapter 7a is derivative estimation. So I guess we'll run through some questions on this, and then hopefully we'll get to nonlinear equations. So this question here, we have this weird expression in terms of, I guess this function f evaluated at different sorts of values. And I guess the idea here is that we want to express this in terms of some constant times the second derivative of f evaluated at a, and some error term involving this difference h that we're plugging in here in various multiples. Yeah, so I guess the approach that the question asks us to use is Taylor expansions. And so if we look over here, we have O of h on this side. And if we're going to Taylor expand these f's, and we have a h squared in the denominator, then the error term that we want in the numerator is going to be cubic, because a cubic divided by a quadratic is going to be linear error term. So to get a cubic error term, we just have to take a degree 2 Taylor expansion. And basically, if you can remember, the formula for Taylor polynomial, which is, hopefully you remember that by now. Yeah, if we truncate it at some sort of term, the error term is just going to be whatever the next degree up is. And this big O is just indicating the sort of relative magnitude of the error term in terms of this difference d. So if we use this formula and we just basically plug it in with varying values for delta, and we crunch the algebra, it turns out the f of a and f prime of a terms will just have coefficients of 0. And so really in the numerator we just end up with this term in terms of f double prime, so the second derivative, and like we wanted, this cubic error term. So if we bring this denominator, we can cancel that with this, cancel that with, I guess, 2 factors of h here. And we end up with this equation. And if we compare that to the right-hand side of this expression, we can see that it matches up exactly where C is 2/3. So that's for this question. So this question had a second part, which was, I guess, thinking more computationally about the problem. And so we're going to set h is equal to 10 to the minus 12, and a is 2 times 10 to the minus 6. And apparently if we do this, we end up estimating f double prime at evaluated a is 0. And I guess the question is the precision that we're using here, double precision, is it accurate enough for this value of 0 for f double prime to be a reasonable value? And I guess the analysis of this setup that's suggested in the solution is basically along the lines of looking at this a plus or minus h value. And this is going to turn out to be this expression here. And then I guess because of floating point rounding error, yeah, so the machine epsilon here, if we go into MATLAB, we can see it's 2 times 10 to the minus 16, approximately. So this a plus or minus h is just going to end up being 2 times 10 to the 6. So all of these inputs to the function are actually going to end up being identical in floating point terms. And because if you look at these coefficients, 3, minus 4, and 1, they add up to 0, this expression is not actually a very good representation of, what this equation is saying analytically. I guess, the mathematical equality here is not really well represented by the floating point representation of these numbers. And so because of this value of 0 is not actually a reasonable guess for f double prime, because this expression is basically a junk value. Cool. Yeah, so I guess this previous expression was a bit funky. This one is a bit more reasonable in practice, I guess. So we're trying to approximate the first derivative of a function at a value. And I guess this question from 2016 is asking us to approximate how big this step size should be for this, I guess, secant approximation to the derivative to give a minimal total error. And we won't be able to exactly compute how big the step size should be, but we'll get an idea of the rough magnitude of how big it should be in terms of the machine precision that we're using. And I guess the thing to know here is that this error is going to come from two different sources. There's the truncation error, which is basically represented by this term, and then there's a rounding error, which is comes about because we're using floating point numbers to compute this expression. So if we take this expression here, the total error is the truncation error plus the rounding error. So this truncation error is just this. And hopefully if h is fairly small, this truncation error will be fairly small because it's just on the order of a linear term in h. And then this rounding error, there's this fact which was discussed in the lectures a little bit more, when we're using a forward difference approximation or a central difference approximation to the first derivative, this rounding error turns out to be just on the order of the machine epsilon divided by the step size. So the thing that the solutions to the 2016 exam suggests is that we basically take these terms inside the brackets representing the magnitude, and we just put coefficients in front of them. And this is probably, I guess it should be a reasonable approximation to the size of this total error. And I guess if we want to minimize this total error, it seems reasonable to minimize this approximation to the total error. And so if we differentiate this expression here, and we set that to 0, and check that the stationary point is actually a minimum, then we can solve for the optimal value of the step size if we want to minimize the total error. And that works out to be this expression here, which is on the order of the square root of the machine precision. And that's a good enough answer for the solutions. We don't need an exact number, we just need the sort of magnitude of how big the step size should be. So this is, I guess, a different way of doing the same thing of approximating the first derivative to a function, and this is the central difference approximation. So in this case, the rounding error will be the same, but the truncation error will be quadratic instead of linear. So hopefully we'll get a slightly better approximation. And if we just run through the same process here of differentiating the approximation, setting the derivative to 0, checking the stationary point is actually minimum, we end up, if we solve for h, we get the optimal step sizes on the order of the cubic root of the machine epsilon. Yeah, so I guess that's how to do these sorts of questions. Okay, so now we'll look a little bit at iterative methods for solving nonlinear equations. So I guess the idea here is we're going to start with some guess for the root of an equation that we want to solve. And we're going to iteratively perform some update based on the previous guess to get the next guess. And hopefully if we do that enough times and the iteration procedure we're performing converges to the actual root, then it should be the case that the more times we do it, the closer and closer we get asymptotically. So one way to look at how fast we get to the root that we want to approximate is this idea of the order of convergence. And we write it in this form, I guess formally, but the idea here is sort of that this, the error of the next guess after k is going to sort of be approximated by some coefficient beta, which is just fixed, times some polynomial term, some polynomial of the previous error. Yeah, and we represent that as this quotient limiting to a fixed beta. And we want beta to be finite and hopefully fairly small. So for Newton's method, where we're basically using the value of the function and the derivative of the function to approximate, where our next guess should be based on the current guess. for Newton's method, the order of convergence is quadratic, which is quite fast. So if we look at this question here, it's asking us to estimate the error after one iteration of the Newton method, given that the Newton method is quadratically convergent. So yeah, if we look at this beta of the next error, beta is the next error divided by the previous error squared in the limit as k gets large. Well, so that's saying that approximately beta is the error of the Newton iterate after x bar divided by the error at x bar squared. So if we move this denominator term over to the left-hand side, then we should have that the error of the next iterate, x bar plus 1, is equal to beta times the square of the previous error. So if the previous error was 10 to the minus 6, then we should have that this is beta times 10 to the minus 12. And I guess it's if we just want a rough estimate, we can sort of assume beta is just 1. And so this will be about 10 to the minus 12 for the next error. Yeah, so this is just a summary of some different iterative methods. So Newton's method we just saw uses the value of the function at the current iterate and the derivative of the function at the current iterate. And this has quadratic convergence. If we don't have a nice way to compute the derivative at the current iterate, we can approximate it by using this difference of, I guess, this secant approximation to the derivative using the current guess and the previous guess. And so if we substitute that into the denominator, we get the secant method iteration formula. And this has an order of convergence a bit less than 2. And this is just the golden ratio. And so in practice in MATLAB, if we want to solve an equation, there's this nice function f0 here. And this uses some, I guess, intelligent logic to pick between a combination of different iterative methods depending on, different, I guess, properties of the approximation problem. So in particular, it uses the bisection method, which we haven't really discussed here. But that is sort of comparable to, I guess it makes use of the intermediate value theorem. And that is, I guess, a fairly slow method. The secant method is a bit better, and the Newton method is, I guess, the best of the three. So I guess maybe we can try, if I look here, so let's say that we want to find a root of x minus 7 to the 3. Well, we know that the root should be 7. But if we pick a stupid first guess, let's make it 1, this will basically perform a bunch of iterations, and once it converges enough to the point that it's not changing the guess very much at each iteration, then it will sort of stop and return us this value of 7, which is pretty good. And we can do this for maybe another function. We could try, I guess, cosine of x starting at 1. And so if we take cosine of 1.5708, hopefully that will be approximately 0. And yes, it's 3 times 10 to the minus 6. On that sort of order of size, which is close to 0. Cool. So that is all for chapter 7. We will cover chapter 8 onwards next week. Yes, and in the meantime, I guess you can ask in the the course chat on the MathSoc Discord if you have any sort of questions or anything you want us to cover on Sunday.